last week we learned quite a few derivative rules. But we didn't learn how to take derivatives of stuff like this. I mean, we learned how to take derivatives of x to the 8th, or 4x squared plus 9, or cosine of x. But if you look at all of these are really composite functions, right? I've got a function to the 8th. I've got a function to the 1/2. I've got a function squared. Okay? Or I could also, probably I should have something like this as well on the board. Because it's not always just to a power. Now I've got the sine of a function. Okay? So these are just some examples of composite functions, and I know how, and what I need to figure out is how to take derivatives of composite functions, because I want to use the derivative rules I've already figured out in order to deal with these things. Okay? So what I really want to think about this in the following way. I want to look at this. Let's take this as a good example. We'll think about this as y of u, right? So if I let u be the inside there, 3x squared plus 9, then y of u is u to the 8th, right? So I'm thinking of the outside function as being the power to the 8th, and the inside function as being this 3x squared plus 9. So I can think about this like that, or with u, or if I prefer, I can also rewrite it as the inside being g of x, and then the outside being x to the 8th, and then my function here, y, is just f of g of x. Okay? Or here I can just write this as y of u of x. So how do I take the derivative of something like that? It's called the chain rule. That's why it says chain rule up there. And I'm just going to write up the rule, and then we're going to do a bunch of examples. I will give you a proof in the extra materials as usual if you're interested in the proof of this. In fact, a really rigorous proof of this can be quite difficult, but we can also get a more relaxed proof of it just to give you the idea. So basically, it looks a little bit different depending on what kind of, what I prefer to use as my notation, whether I use the primes or whether I use the dy dx's. I personally prefer the dy dx because it's easier to remember. So my rule is that if y is written like this, dy dx is dy du du dx. Okay? So that's actually kind of easier to remember because you can kind of mentally think about it. Okay, the du's cancel out. Though that's not really what's happening because we're not thinking about these things as fractions. We're just thinking about it as a notation. But anyway, it helps us remember. Otherwise, if I'm here, I can write this, the derivative y prime. It's the derivative of the outer function when the inner function stays the same, and then I multiply it by the derivative of the inner function. Okay? So either of those two forms, it's the same thing, and you'll see it's called the chain rule because you end up forming a chain of these things. When it's only two, it's not such a big thing, but we can do it again and again and again. You can have a function that is there's like outside function, inside function, inside function, inside function, and you just end up with a chain of all of them. We will do some examples like that. There are some examples like that on the homework on the worksheet. But for start out, we'll start it with some easy ones. So to be very clear, you can write it like this with the u if you want. So I'll actually do that for this very first one. But typically, well, I don't do it that way. I just sort of go ahead and take the derivative of the outer, inner. So, but if we want to actually explicitly look at this, with this example, dy du, so we have, it's this one we're doing, right? This one, we'll get to those later. So dy du is going to be 8u to the 7th du dx. That's the inner part, so that's just going to be 6x. So when I look at the whole thing, I get 8u to the 7th times 6x, but u is that 3x squared, so I ended up, I'm going to put that in there, and I'm just going to put these together. The 8 times the 6th. 3x squared plus 9 to the 7th. Okay? So if I break it up like those that way, I can do it that way. On the other hand, if I want to sort of not explicitly write it as a u, I'm going to get rid of this for a second. Let me show you how I would do it without explicitly writing the u, but just sort of thinking about it as the outer function times the inner function, the derivative of the inner function. So what I would do is I would, in my mind, think the outer function is the power to the 8th, u to the 8th. What do? I take the derivative of that whole thing. I'm just leaving this in there. Times the derivative of the inner function. So this is how I will usually write them. And this is how I will usually do them. If you want to explicitly write it with the u, you're welcome to do so. You'll notice that I'm thinking about what the outside function is, the power to the 8, and the stuff in the inside at first doesn't change. I don't take the derivative and put it inside the power, right? I leave the inside the same, and I multiply by the derivative. So it sort of moves this way. It's not all together. So let me do another example. I'm just going to do these examples here, and then in another video we'll do some more complicated examples. Okay? So for this next one, I'm just going to write it like this. Y equals 4x squared plus 9 to the 1/2. Okay, so this is very similar to the previous one, except instead of an 8, we have a 1/2, right? So, but it's still, you're still doing the power rule, so it would be 1/2 times my inner function to the negative 1/2, right, and minus 1. And then I'm going to take the derivative of that inner function. Okay, so that is going to, and I'm just going to like rewrite this a little bit. This is 4x squared plus 9. And then the derivative here is going to be 8x, right? And then I can, do a little bit of cleaning up. Like so. Okay. All right, so next one, cosine squared. So cosine squared x, now we have also fairly similar. I do want to remember when I have cosine squared x written this way, it means this, right? So my outer function here is the square. So it would be y prime would be 2 times cosine x, right, to the 2 minus 1, right? So it's just to the power of 1, times the derivative of the cosine of x. So it's always you're going to take the derivative of what's the function inside the parentheses. So this is 2 cosine x, and derivative of cosine is negative sine. So there's my answer. And I can just leave it like that. If you want to make it something else, if you want to say, oh, that's sine of 2x, okay, fine, it's not wrong. You can just leave it that way. Before we do this one, let's contrast this to cosine of x squared. So again, I have a squared, but now the squared is on the inside of the argument. So whereas here my outside function was the power and my inside function was cosine, Here, my outside function is cosine, and my inside function is the power. So when I do my derivative, I'm going to do the derivative of the outside function, so that is the derivative of cosine, which will give you minus sine. So I'm going minus sine of x squared, and then I have the derivative of the inside function of what's inside the parentheses, so that's the derivative of x squared. So when I do that, I'm going to get 2x, right? So I end up with an answer that looks like this. So the functions they look pretty similar, but they are very different, right? And so our derivatives then, again, are very different. Okay. Oh, last one. Let me do this last one. I didn't realize there's another one there. This is a quick one, though, right? Sine of something. Since we did the x squared, this one, very similar. The derivative of sine is cosine. What's in the parentheses stays the same. I take the derivative of what's inside the parentheses. It's just going to be 5. So I have 5 cosine 5x plus 9. Okay? Now you can see, though, whenever you have anything inside the parentheses besides x, you have 2x, 10x, whatever it is, you're going to end up with an additional factor in the front due to taking the derivative of what's inside the parentheses.